the largest, most powerful, and most complex space telescope ever built.
James Webb.
James Webb.
James Webb Space Telescope.
James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth. The posts claim that the telescope captured the object changing its trajectory.
Far beyond the orbit of Neptune, in the silent reaches where sunlight is faint and the cold of interstellar space begins to take hold, something extraordinary has just unfolded. The James Webb Space Telescope, humanity's most advanced eye on the cosmos, detected an event so rare and dramatic that it challenges our understanding of interstellar objects. 3I Atlas, the third known interstellar visitor to pass through our solar system, has just experienced a colossal collision. The detection was not just a fleeting trace or a vague anomaly. It was a definitive and spectacular signature of energy, debris, and transformation on a scale that very few instruments could have captured. Webb's unmatched infrared sensitivity revealed the exact moment something massive collided with this enigmatic traveler from another star system. Before we start, smash the like and subscribe buttons for more updates.
3I Atlas was discovered on July 1st by the NASA-funded Atlas survey.
The very existence of 3I Atlas was already a profound mystery before this event. When it was first identified, astronomers recognized it as belonging to the same rare category as 1I Oumuamua and 2I/Borisov, a body not bound by the gravity of the Sun, originating from somewhere far beyond our stellar neighborhood. Its trajectory told us it was just passing through, never to return, a messenger carrying the ancient history of another solar system embedded in its composition. To witness such an object undergo a catastrophic collision within our observational reach is nothing short of astonishing, because the probability of such an encounter occurring in the vastness of space is astronomically small. And yet, against all odds, it has happened, and Webb was there to see it. The telescope's data indicated a sudden flare in thermal signatures, followed by an expanding halo of material dispersing into space. This was no subtle event. Something enormous, possibly a rogue planetesimal, a massive comet-like body, or a chunk of interstellar debris intersecting its path, slammed directly into 3I Atlas. The immediate aftermath of the collision created a glowing envelope, a plume rich with ices and silicates that briefly transformed the dark, lonely rock into a beacon against the black of interstellar space. To detect this in real time means Webb's instruments were perfectly positioned, as if fate had arranged for humanity's telescope to look in the right place at the right moment. The implications are staggering. Interstellar objects like 3I Atlas are priceless to science because they are relics of other planetary systems, fragments ejected during the chaotic epochs of planet formation billions of years ago. They are pristine time capsules that carry with them the chemistry and conditions of alien suns and planets. To see one collide with another body grants us the opportunity to peer inside, to study its interior makeup in a way we never imagined possible. The ejected material, spreading outward in a dusty shroud, carries the fingerprint of its parent system, revealing molecules, isotopes, and structures that could never be discerned from surface reflection alone. This is a natural experiment of cosmic proportions, one no laboratory on Earth could ever replicate. The violent energy of the collision also raises questions about the mechanics of interstellar travel. For an object to collide with 3I Atlas at such velocity suggests that interstellar space, often imagined as empty, may hold far more traffic than we assume. Streams of debris may drift between stars, remnants of shattered worlds and orphaned comets tossed out by gravitational interactions. The fact that Webb captured such an interaction suggests that interstellar space is not as serene as it appears, but instead a dynamic environment where cataclysmic interactions can occur even millions of years after an object has been flung from its home system. This changes the way we think about interstellar migration and the lifespan of planetary fragments on galactic journeys. What makes this moment even more electrifying is the potential for discovery locked within the collision's plume. Webb's spectroscopic instruments are capable of analyzing the light passing through the ejected dust and gases, isolating the chemical signatures with exquisite precision. Already, preliminary data hints at exotic carbon chains, frozen volatiles, and heavy metals that have rarely been observed in such combination. This is a treasure chest for astrophysics, a chance to directly sample the chemistry of another solar system without leaving our own. Each molecule detected tells a story, a whisper from another star, a piece of the puzzle about how planets form, how life-essential compounds arise, and how common such processes may be across the galaxy. The sheer size of the collision adds another layer of intrigue. For such a dramatic energy release to occur, the impacting body had to be massive. It could have been a fellow interstellar fragment traveling on its own hyperbolic path, or even something long orbiting in the outer reaches of our own solar system, unseen until now, finally intersecting with 3I Atlas. The geometry of their meeting is as breathtaking as it is improbable, a cosmic accident that unfolded at just the right place and time. The collision's brightness lingered long enough to suggest that enormous amounts of material were vaporized, glowing with heat before dispersing. Such a spectacle may remain visible in different wavelengths for weeks or months, giving astronomers a window to continue studying the aftermath in detail. The event also underscores the unparalleled power of the James Webb Space Telescope. Ground-based observatories would never have caught the fine-grained infrared glow that marked the first signs of impact. Even Hubble, legendary as it is, would have struggled to parse the dim, fast-changing dynamics of the scene. Webb's sensitivity to faint light, its ability to cut through the cold of deep space, and its position beyond Earth's atmosphere all combine to make this detection possible. It is a triumph not just of technology but of timing, a reminder of why humanity invests in such ambitious instruments. Without Webb, the universe would have kept this secret hidden forever. The broader implications for planetary science are immense. If collisions between interstellar objects are more common than expected, then our galaxy is littered with the fragments of endless cosmic accidents. Each star system not only ejects debris, but also hosts the possibility of violent encounters that continually reshape these wandering bodies. This means that interstellar visitors are not untouched relics, but evolving artifacts, their surfaces scarred and their compositions altered by impacts across unimaginable distances. Understanding these processes helps refine our models of solar system evolution, shedding light on how chaos and destruction contribute to creation and diversity. The energy of the collision also illuminates the scale of forces at play in the interstellar medium. Unlike slow encounters within the gravity wells of planets, interstellar collisions happen at relative velocities that dwarf anything seen in familiar orbital mechanics. The kinetic energy unleashed when two objects traveling tens of kilometers per second collide is beyond comprehension, enough to pulverize rock, vaporize ice, and send fragments scattering across light years. To witness such a release is to glimpse the violent undercurrent that lies beneath the calm appearance of the night sky. Stars may twinkle serenely from Earth's perspective, but in the darkness between them, unimaginable cataclysms unfold. 3I Atlas, once a mysterious wanderer, is now transformed into a symbol of cosmic drama. Its collision is not merely an isolated event, but a doorway into new realms of understanding. For the first time, we have seen an interstellar traveler stripped bare, its secrets cast outward by violence. The timing could not be more fortuitous. Humanity is at a stage where our instruments are finally sensitive enough to catch such fleeting moments, where our theories are advanced enough to interpret the data, and where our curiosity drives us to search for meaning in every speck of dust illuminated by distant light. As the debris cloud expands, astronomers will continue to track it, unraveling layer by layer the story encoded in its composition. Each passing day of observation offers a deeper glimpse into the chemistry of alien worlds, the processes that shaped them, and the chaotic journeys that brought their fragments into our skies. The collision is not just a cosmic accident. It is a revelation, a chance to see the universe both as it is and as it has always been, dynamic, unpredictable, and filled with wonders beyond imagination. The collision between 3I Atlas and its mysterious cosmic partner reverberates as a moment of singular importance in the story of astronomy. But the deeper one digs into its layers, the richer and more compelling the narrative becomes. While the initial detection spoke of energy, light, and matter erupting in the dark, what follows in terms of meaning and possibility takes the discovery to entirely new heights. The sheer improbability of such a collision, its scientific harvest, and its resonance with the broader questions of cosmic origin and interstellar destiny all deserve to be unraveled carefully. The further this moment is stretched under the lens of imagination and scientific insight, the more it transforms into something far larger than a singular astronomical event. To begin with, the improbable geometry of this event deserves far more attention. Space is often depicted as an endless void where even galaxies are separated by gulfs so vast that light takes millions of years to cross them. Within such immensity, the odds of two solid bodies colliding, especially when one of them is a known interstellar interloper, are almost vanishingly small. For context, in our solar system, countless asteroids and comets circle the sun, and yet major collisions between large bodies are exceedingly rare. Scale this up to the galactic level, where trajectories are less constrained and paths more erratic, and the thought of such an intersection seems almost impossible. And yet, impossibility is the wrong word here because given enough time, the unlikely is destined to occur. What the James Webb Telescope captured is one of those impossibilities realized, a reminder that the universe is not a static theater, but a restless stage of constant motion where even the most improbable events eventually unfold. The object itself, 3I Atlas, deserves more than a passing glance in this narrative. Its very name marks it as a member of a rare class, the I signifying interstellar, the third of its kind to be detected. Each of these objects has carried its own peculiarities. Oumuamua baffled astronomers with its elongated shape and unexpected acceleration, prompting speculation ranging from natural explanations to outlandish theories of alien craft. Borisov resembled a more conventional comet, albeit one with unusual composition, bringing with it a clear signature of another star's planetary nursery. 3I Atlas continued this tradition of surprise by appearing less like either of its predecessors and more like a hybrid, a body with the reflectivity of an icy surface but with dynamic behavior hinting at rocky or metallic content. Already it was unique, and now its collision has revealed even more extraordinary properties. One of the most fascinating aspects of this event is how the material ejected by the collision provides a direct window into the object's inner chemistry. Normally, telescopes only see the reflected sunlight from the surface of such distant bodies. That light can reveal something about surface color, albedo, and perhaps traces of molecules, but it is far from enough to decode the whole story. A collision, however, acts like a natural dissection. The crust of the object is ripped apart, exposing its core to the scrutiny of infrared and spectroscopic instruments. With Webb's ability to analyze spectral lines in exquisite detail, scientists can now distinguish the fingerprints of water ice, organic molecules, silicate minerals, and perhaps even metals hidden beneath the surface. This information is gold dust for planetary scientists, because it offers not just a snapshot of one alien rock, but a sample from the building blocks of an entire planetary system elsewhere in the galaxy. The cosmic violence of such a collision also invites reflection on the role of destruction in creation. On Earth, collisions shape the trajectory of life and geology alike. The Moon is thought to have formed from a colossal impact billions of years ago, and the extinction of the dinosaurs was triggered by a cosmic strike from a much smaller asteroid. On a galactic scale, collisions between interstellar bodies may scatter the very seeds of planets and even life. Every rock shattered becomes a cloud of dust, and every dust grain may drift into new star systems, contributing to the raw material for planets, atmospheres, and eventually biology. The plume from 3I Atlas may someday travel across light years, and though no living being will trace its path, the matter it casts outward may be woven into new worlds around distant stars. The James Webb detection thus captures a fleeting explosion but also freezes in time one link in the eternal cycle of destruction and rebirth that animates the cosmos. It is also important to appreciate how the Webb telescope itself elevates this event into a turning point. With its golden mirrors and infrared instruments, it is uniquely suited to detect the faintest signals of heat and dust in space. Without Webb, the flare from the collision might have gone unnoticed, blending into the background of cosmic radiation. Instead, humanity has, for the first time, observed in detail what happens when two interstellar bodies meet. This not only validates Webb's design as a tool for probing deep space, but also showcases the way chance and technology align to make history. Such detections cannot be planned in advance. They are moments of serendipity, of being ready when the universe decides to perform. The lesson is profound. Our instruments must always be looking, because the cosmos does not schedule its revelations. The implications for astrophysics extend beyond chemical composition. The trajectory of the debris cloud will be mapped carefully in the coming months, and from its dispersion, astronomers will infer the energy of the collision, the mass of the impacting bodies, and the density of the ejected material. These calculations will help refine models of interstellar dynamics. For instance, if the impacting body was another interstellar fragment, this suggests that the galaxy contains countless such wanderers, far more than current detection rates imply. This could mean that planetary systems eject far more material during their formation than previously thought. If, on the other hand, the colliding body was a hidden resident of the outer solar system, perhaps a massive object in the Oort cloud or beyond, then the discovery could provide indirect evidence of a local population of large, distant bodies that we have yet to chart. Either scenario radically changes our understanding of what drifts unseen in the cosmic dark. Another remarkable layer of this event is how it reframes humanity's sense of cosmic connectedness. Each interstellar object that passes through our solar system is a messenger from elsewhere, carrying matter that once belonged to a star and planets unimaginably far away. By colliding within view of our instruments, 3i Atlas has shared its secrets with us, whether intentionally or not. It bridges the gap between the known and the unknown, between our sun's family and the wider stellar community. Every molecule of carbon, every atom of oxygen in the debris cloud tells us that the processes shaping worlds are universal, not limited to our sun's orbit. They happen everywhere, under countless stars, following the same physical laws, but yielding infinite variations. The significance of organics in particular cannot be overstated. If Webb's spectrographs reveal complex carbon compounds in the ejected material, it would confirm that the building blocks of life are not rare, earthbound oddities, but galactic staples. Such a discovery would reinforce the idea that the conditions for life are written into the very chemistry of star systems, waiting for the right environments to spark biology. This does not prove life exists elsewhere, but it erodes the notion of Earth as uniquely blessed. Instead, it frames us as part of a cosmic continuum where collisions, chemistry, and chance combine to make life possible across the galaxy. The energetic nature of the collision also touches on the physics of high-velocity impacts. Interstellar objects travel at extraordinary speeds, often tens of kilometers per second relative to the Sun. When two such objects meet, the kinetic energy released dwarfs anything human engineering can create. Nuclear explosions pale in comparison to the raw power of such an event. The heat vaporizes ice into vast clouds of steam, shatters rock into shards that glisten in infrared, and blasts metals into plasma. Webb's instruments can observe these transformations, but to grasp their scale requires imagination. One could picture entire mountain ranges pulverized in the blink of an eye, entire oceans of ice vaporized into nothingness. It is violence on a scale that reminds us how small and fragile our own world is in the face of cosmic mechanics. Equally important is the philosophical dimension of this event. For centuries, humanity has looked at the stars with curiosity, crafting myths, theories, and instruments to interpret their light. Each milestone, from Galileo's telescope to Hubble's deep fields, has peeled back another layer of the cosmic onion. Now with Webb, we have not just seen distant galaxies or ancient starlight, but have captured a fleeting act of interstellar drama. This bridges the abstract and the tangible, reminding us that the universe is not just a backdrop for human life, but an active, evolving environment where events unfold independently of us, yet still touch our existence. The collision of 3i Atlas does not change human life in direct terms, but it expands the horizon of what we know is possible, and in doing so, it enriches the meaning of our place in the cosmos. The cultural resonance of such a discovery should not be underestimated either. Humans are storytellers, and every astronomical event becomes part of a larger narrative about who we are and where we come from. Just as ancient people saw omens in comets and eclipses, modern humanity sees revelations in data streams and spectral lines. The collision of 3i Atlas will likely inspire new questions in art, literature, and philosophy just as much as in science. It captures the imagination because it is both deeply alien and strangely familiar. Rocks colliding just as they have for eons in our solar system, but here carried out in the context of a vast galactic stage. The scientific community, too, will feel the ripple effects for decades. The collision provides a natural laboratory for testing theories of planetary formation, interstellar chemistry, and high-energy astrophysics. Graduate students and seasoned scientists alike will pore over the data, drawing out insights, challenging assumptions, and proposing new missions to chase the debris or watch for similar events. Each question answered will give rise to 10 more, fueling the cycle of discovery that defines science. This is how progress is made, not in steady increments, but in leaps driven by rare and transformative events. Perhaps most thrilling is how this detection reshapes the way we think about the abundance of interstellar objects. Before Oumuamua, none had ever been observed. With Borisov II, the idea of interstellar visitors was confirmed as a reality rather than an anomaly. 3I Atlas reinforced the notion, and now, with its collision, it has opened the door to the idea that the galaxy is teeming with such bodies, many of them colliding, fragmenting, and dispersing their contents into the void. If so, then our solar system is constantly being brushed by the fingerprints of other stars, each passing object leaving subtle marks in the form of dust, debris, or even meteors. The boundaries between systems are not walls but porous borders, crossed regularly by travelers carrying the stories of their origins. The Webb telescope has, in essence, caught the universe in the act of storytelling. It has witnessed not just light from ancient galaxies or faint signatures of exoplanet atmospheres, but the dynamic moment when matter from one star system collides with matter from another. It is a moment that embodies the essence of astronomy, the study of change across scales so vast they defy comprehension. The 3I Atlas collision is not just another data point, but a turning point, a reminder that the universe is alive with motion, surprise, and meaning. And as scientists continue to study the expanding debris cloud, humanity itself will continue to be transformed by the knowledge. For every atom of oxygen or molecule of carbon dioxide identified in that cloud, there will be echoes of recognition. We breathe oxygen here on Earth. We build our cells on carbon. In the ashes of a collision billions of miles away, we find reflections of ourselves. This is the ultimate gift of astronomy, not just to reveal the unknown, but to show us that the unknown is, in some sense, already part of us. The enormity of the collision involving 3I Atlas cannot be overstated. And yet, even after considering its rarity, its chemical revelations, and its philosophical weight, there remain deeper dimensions to unpack. The event sits at the crossroads of cosmology, planetary science, and human imagination. Its importance grows not just from the physics of the collision itself, but from the windows it opens into areas of research, into cosmic history, and into the way humanity envisions its future among the stars. Far from exhausted, the story of this single astronomical detection continues to branch outward, touching areas of inquiry that stretch from the microstructure of dust grains to the architecture of galaxies themselves. To begin with, this event highlights the fact that our galaxy is far from a static backdrop. The Milky Way is a vast ecosystem in motion, where stars orbit the galactic center, nebulae give birth to suns, and matter continually shifts between states. Within such a system, collisions are not rare exceptions but recurring motifs. Galaxies collide with each other, stars occasionally graze past one another, and smaller objects like 3I Atlas weave unpredictable courses between them. The Webb detection illustrates this principle vividly. Even on the level of kilometer-scale bodies, the galactic ballet produces interactions that shape the destiny of matter. Each impact is a thread woven into the tapestry of cosmic evolution, redistributing elements and reshaping structures that will someday form new stars or planets. Seen in this light, the 3I Atlas event is not a solitary accident, but a microcosm of the galaxy's ongoing dynamism. Just as mountain ranges on Earth are shaped by tectonic collisions, so too is the galactic environment sculpted by encounters between its smallest constituents. It reminds us that no scale is too small to matter, and that the drama of creation and destruction permeates the cosmos at every level. An often overlooked aspect of such detections is their relevance to the practical field of planetary defense. Humanity has long been concerned about the risk of asteroids or comets striking Earth, an anxiety heightened by the historical record of impacts and the recognition that planetary-scale collisions can have catastrophic consequences. Observing 3I Atlas undergo a collision provides an unprecedented laboratory for understanding exactly how bodies fragment under high-energy impacts. The debris cloud expanding from the impact can teach scientists how material disperses, how much remains intact, and what sizes of fragments are produced. Such knowledge can be directly applied to strategies for deflecting or destroying dangerous asteroids near Earth. By comparing models of controlled deflections with real data from a natural interstellar collision, humanity gains a more accurate picture of what would happen if we ever needed to nudge a threatening body off course. The data is not just academic, it could one day safeguard civilizations. Another profound angle lies in how this event forces us to reconsider the very origins of matter in our solar system. Every element heavier than hydrogen was forged in the cores of stars or in the violent crucibles of supernovae. These elements were scattered into interstellar space, later incorporated into clouds that collapsed into new stars and planets. When an interstellar object like 3I Atlas passes through our neighborhood, it represents a sample of this process carried out under entirely different conditions. By colliding, it revealed its composition not just as a frozen relic, but as a dynamic participant in the cycle of matter. Studying its dust cloud allows scientists to trace the pathways by which alien systems incorporated and redistributed their elements. Was the oxygen bound in water ice or in silicate minerals? Were carbon chains long and complex or simple and unformed? The answers help distinguish whether the processes that seeded life on Earth are commonplace across the galaxy or rare flukes. In other words, the plume of dust from 3I Atlas is not just debris. It is evidence in a cosmic investigation into how universes of planets and life emerge. Beyond science, the collision invites speculation about humanity's future ambitions in space exploration. When visionaries dream of sending probes or even crewed missions to other star systems, they confront the immense distances and the dangers of interstellar travel. One of the greatest risks comes from collisions with small but fast-moving objects. Even a pebble-sized rock at interstellar speeds could obliterate a spacecraft. The collision of 3I Atlas offers a vivid demonstration of what happens when bodies meet at such velocities. Observing the energy release and material behavior in such a case helps refine the engineering needed for future missions. Shielding concepts, trajectory planning, and risk models can all be tested against the lessons learned from this natural experiment. In a sense, 3I Atlas has performed the first stress test of interstellar navigation in front of our eyes, giving us data we would otherwise only guess at. One of the most remarkable elements of this story is the role of chance. The cosmos is vast, and yet the Webb telescope was positioned and active at precisely the right moment to record this collision. This serendipity highlights the unpredictable nature of discovery. It raises the question, how many other such events go unnoticed, occurring far from our gaze or in wavelengths our instruments cannot yet detect? This realization is sobering but also inspiring. It underscores the need for constant vigilance, for networks of instruments always scanning the skies. If Webb alone could capture this, imagine what an array of equally advanced observatories might uncover. The collision is both a triumph and a call to expand humanity's observational reach to ensure that more cosmic secrets are not lost to silence. Dust may seem insignificant on Earth, but in cosmic terms, it is the currency of creation. Every star system forms from dust. Every planet begins as grains colliding and sticking together. The plume from 3I Atlas has released an entire economy of dust grains back into interstellar circulation. Over millions of years, these grains may drift far beyond the site of the collision, spreading the materials of one solar system into others. This raises the fascinating possibility of panspermia at the galactic level. If dust grains carry organic molecules, then they serve as vessels for distributing the precursors of life across the stars. The 3I Atlas collision may have just injected seeds into the galactic winds, seeds that could someday fall into the cradle of a new world. The cycle of matter thus becomes more than chemistry. It becomes a quiet story of potential biology on a cosmic scale. Another angle to reflect on is how the rest of the solar system, or even other nearby stars, serve as silent witnesses to such events. Light travels in every direction, and though Webb captured this collision from its station at L2, countless other vantage points exist. Imagine distant civilizations, if they exist, observing the same flare of energy with their own instruments. For them, the event would hold as much fascination as it does for us, a shared astronomical drama unfolding across light years. This thought deepens the sense of cosmic community. We are not alone in watching the universe perform. Every collision, every nova, every eclipse is a universal spectacle, witnessed from different corners by any who have the means to look. 3I Atlas may be more than a messenger of alien systems. It may also be a shared signal, a cosmic event that ties observers together in the act of discovery. On a more technical level, the detection forces astrophysicists to revisit long-standing models of interstellar object behavior. Until now, most simulations of such bodies assumed that they traveled through space largely undisturbed, their greatest changes occurring during close approaches to stars. A collision of this magnitude challenges that assumption. If such impacts are even moderately frequent, then interstellar objects may not be the untouched fossils we imagined. Instead, they may be scarred, fragmented, and chemically altered by interactions over the course of their journeys. This shifts how we interpret the data from future interstellar visitors. Rather than assuming pristine records, we must account for histories of violence, for layers of impact mixing and heating that blur the signatures of their origins. This complicates analysis but also makes it more intriguing, adding depth to each object's biography as a wanderer shaped not only by its birth system, but by the accidents of its travels. The story of 3I Atlas is also in some ways a mirror for human history. Civilizations too are shaped by collisions between cultures, ideas, and technologies. These encounters often appear violent or disruptive, but they also release new energy, new creativity, and new combinations that carry humanity forward. Just as the dust of 3I Atlas spreads its secrets across the void, so too do the fragments of human encounters spread across the world, generating unexpected futures. In this way, the collision becomes a metaphor, reminding us that destruction and transformation are intertwined forces. We cannot avoid the chaos of the cosmos, nor the upheavals of our own histories, but we can learn from them, draw meaning from them, and allow them to enrich the tapestry of our understanding. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on James Webb spotting something huge with 3I Atlas? We want to hear from you. Thank you for watching, and see you next time.